Okay, thanks very much, Mark. Welcome, everybody. I'm glad you've managed to survive till the kind of 10th hour. Of course, we saved the best till last here. We got Ginger following me to close the event out, and then I'm going to try and do a quick lap around Spark here. Mostly because I was looking at Mark's session list and I went, there's nobody talking about Spark. So I decided to pick that up. I'm Euan Garden. I'm a principal program manager. I work on the Azure Data OSS Analytics team. My team produces Synapse Spark, HDI Spark, HDI Kafka, HDI HBase, LLAP, Hive, all that kind of stuff. And so I'm going to talk today about Spark and specifically inside of Synapse, because we do a few things differently there that we don't expect to see normally in implementations of Spark. So I'm going to try and explain what we do differently, why we do it differently, and then we'll take a look at it and we'll talk through some implications of some decisions when you're creating your Spark pools, which is the unit of kind of definition. And then we'll look at some demos of various different parts of the product and we'll kind of bounce around a little bit. Okay, so what are the principles behind Spark in Synapse? So when we set out to build Spark in Synapse, we had a ton of experience with just regular, what we call provisioned clusters inside of HDI. We'd seen what the industry was doing. And so we very specifically, oh, I apologize if you can hear my dog. He's being intimidated by either a fly or a leaf. I can't tell which one it is right now. So we wanted to do things a little differently, which allowed us to be more efficient. And one of the pieces of feedback we got was, well, ADLA didn't really take off as a product. People love the idea of the notion of a job service and clusterless clusters, is what we used to call them back then. And so what we've tried to do is replicate some of that, but to do it with a Spark and an integration into Synapse capability. So first of all, we talk about the service as a managed job service. You don't have to worry about updating nodes and security patches and all sorts of things like that. You don't have to worry about being on the latest build. We handle all of that for you. And by job service, I mean our clusters are designed to be shut down most of the time. And they're designed to say, hey, if there's work coming in, I'll wake up. But if there's no work, I'll just have a little snooze. And you don't pay for them. Particularly Spark pools, which is the definition, which we'll go through in a second. You don't pay for those. You can have as many of those as one. You can have one, you can have 100. It's all your choice. And so a job service means we send work to the service. It does the work. It checks the queue after it's finished its work for some amount of time that you specify. And if there's no new work, then it automatically shuts itself down. It will also auto scale down during that same time frame so that you're not paying for all the nodes while it's waiting to see if there's more work coming in. And we'll also auto scale up. So we'll really try and manage your resources. And we scale in two different dimensions that I'll talk about in a little bit. So the clusters are what we call fast start shutdown. And I'll explain a couple of tricks that we use to enable them to start so fast. Today, we're about 2.5 to 3.5 minutes. So I thought we're closer to 2.5 these days. We're going to work to drive that down. The team has pulled off some fairly significant magic tricks to get down to a 2.5 minute start. And we think we've got a little bit more we can squeeze out before we have to do anything dramatic with the architecture. And the shutdowns are almost instant. And it doesn't matter whether it's what we call a static cluster or an autoscale cluster, which I'll also describe. You have limited control because it turns out when you let people SSH into the head nodes of your cluster, all sorts of weird and scary stuff can happen. And we've learned that from supporting HD Insight over the last few years that, we'll log into, somebody will send us a support call and we'll say, what have you done to the cluster? And they're like, nothing. And then we'll go in and we'll find all sorts of background processes running, all sorts of cron jobs running and things like that. And so we simply don't allow that. We also don't allow startup scripts because that's a way around some of the security that we have. People would install new versions of Python and all sorts of things like that as part of the startup scripts. So today we don't have startup scripts. It's something that we'll keep looking at because they are used pretty heavily, but they're mostly used on HD Insight side for library management, so adding additional Python or Scala libraries into the system. And we have a different way of doing that that's a managed way of doing it. I always see lots of questions, which is, hey, is Synapse just using Databricks under the covers? And the answer is absolutely no, it's not. We take the open source distribution of Spark directly from Apache. We use the same branch for HD Insight and for Synapse, and we're working to merge the big data clusters version of Spark in there as well. So it'll be one distribution that we call Clear Lake from Microsoft. And we take that core distribution and we add a bunch of stuff to it. Now, some of that stuff is things like connectivity to other Microsoft services. So we want great connectivity to Azure Data Explorer. We want great connectivity to Cosmos DB. So there's a whole bunch of things like that we add. We also do a ton of performance work. And we had a great blog post that we posted, I guess, a month ago now, which had tens of thousands of views that explains what some of those enhancements are and how we did them. And one of the big things that we can do is we have members of the SQL Server team who worked on SQL Server's query processor for 15 plus years on the team. And so they're able to take some of the relational optimizations that we've done and apply them to Spark, things like Bloom filters, which was a big hit. And when we did that in terms of performance impact. We're also able to take ideas from open source and from other teams, like the LinkedIn team has a very mature Spark implementation, and do things like dynamic partition pruning, which is now a feature of Spark 3.0, but we did an implementation on 2.4. Our goal is also to support the least numbers of Spark possible. While it's really cool that in a bunch of other places you can choose from 12 different versions of Spark and 4 different versions of Python, it creates a supportability headache that means we can't do as good a job of optimization and supporting. And so the goal is to support a relatively small number. Today we have 2.4.x, we call it, because we don't let you choose the build number. We choose that, and we will upgrade it in the background as part of being a managed cluster for you. And then on the other side, we have a preview of Spark 3.0. It's based actually on Spark 3.0.2, to be honest. But again, we're not going to let you choose the build number. But when we GA that, it'll be based on a build of Spark 3.1. There's some performance optimizations and some scheduler changes that we want to take from the 3.1 code base. So that's where we are with different capabilities. The most important feature of Synapse Spark, however, is actually the fact that we deeply integrate with Synapse. There's all sorts of things like managed VNets. Weihong was talking about managed VNets for ADF. It was a lot of work to get managed VNets up and running on the Spark side, and to get things like library management working, and where we download directly from Conda or from pip, to get all that working, especially with what we call data exfiltration protection on the network. And so that integration is critical. And one of the big things that sometimes catches people out is we are not a high concurrency serving platform. So lots of people do their data preparation inside of Spark, and then the data's there, is lying around on disk, and then they connect it from Power BI or from a custom app. We don't believe that Spark is a great serving platform, particularly not at high concurrency, because of the cost of managing it and leaving it lying around as a provisioned cluster. And it also doesn't fit with the managed job model that I talked about earlier on. And so we're not designed to do that. And in fact, as a way of enforcing that, there is no ODBC or JDBC access to our Spark instances right now. Now, that's always under review based on feedback from ISVs and other teams, excuse me, but we hope that it was something we don't have to add, because it has a whole bunch of implications on the back-end scalability of the system that we have to address. Excuse me, I'll drink a little water here. Now, our answer there is you can use Livy to submit batch sessions to the Spark instances, and that's a fairly common API that's used very heavily, but it's batch, not interactive. And then the other answer is to go ahead and take your results at the end of your data prep phase and write them back into the lake, which most people do anyway, whether for audit purposes or caching purposes, and then to query with them directly with something like SQL Serverless or SQL Dedicated. In both cases, those are designed to be high concurrency serving platforms, which use a T-SQL endpoint, which means that pretty much every tool on the planet, every client app knows how to connect and knows how to send SQL to it, as opposed to Spark SQL, which is slowly getting closer and closer to ANSI SQL compatibility. All right, so let's take a pause there from the slides and we'll go into the product.
So we had a question about if single node Spark pools would be on the roadmap or supported in the future.
It is something that we're looking at doing, yes. It's a little challenging to do right now with our infrastructure, and you'll see that in a second, why it might be challenging when I go back to the slides. But yes, it's a big ask that people have, and it's something we're looking at how we can go ahead and do. All right, so let's go ahead and let's create something called an Apache Spark pool. So here you can see I've got a bunch of them, and you can see what sizes they are. Some are scale, some are static in terms of how they work, but we're going to go ahead and create our own. So let's call it Data Toboggan Demo. Okay, very inventful name in my case. And that's actually all I need to do. Now I can do a whole bunch of customization, and we're going to go through that customization in a second. But I can just go ahead and hit review and create at this point in time if I want to get up and running quickly. And that's one of the principles what we're trying to do here. You'll see from this creation experience for Spark pools that there's not that many choices. We're going to make smart defaults where we can, and we'll simplify things where we can, and I'll identify some of those opportunities as we go through here. Now, this thing that we call a Spark pool is not a cluster. It is a metadata definition of what you want a cluster to look like. We'll come back to the slides and we'll explain how that works and why it works that particular way. But just think about it as saying you connect to it as if it were a cluster. It's not actually a running cluster. And when you connect to it, you're saying, hey, if there's one of these running with my identity, please go ahead and connect me to it. And if there's not one running with my identity, please go ahead and take 2.5 minutes and create it for me. Okay, so node size family, we only support, thank you. That would be a little bug in the UI. There we go. Demo, probably didn't like the full name. And so here we have memory optimized is the only SKU family we support, because one of the pieces of feedback we've had is when you drop those combos down, which most products in Azure have, and you get a list of 200 SKUs, people don't know which ones to take. And so we've chosen what we think is the best price performance SKU in Azure. And it has been for the last 1.5 years that we've been developing, although we're actually about to upgrade it. But you won't notice, you won't pay any more. But under the covers, things should get faster, particularly I/O, but also, excuse me, a little bit of CPU. And that's part of being a managed job service. We'll choose the hardware for you, and we'll choose the best one, and we'll keep evolving that hardware over time and worry about capacity planning and all those things at the Azure level. We are going to add support for GPUs. We announced a private preview of GPU support, initially with the NVIDIA T4 SKU, which is very good at doing actually data prep and ETL and scoring of ML models. And then we're going to add the higher end SKUs at a later point in time, which will do training of DNN models. The other SKU type we'll add is an FPGA SKU. We've been doing some experiments with using FPGA to crack open CSV files and Parquet files, and they are way faster, and also FPGAs are remarkably cheap, it turns out. Now let's turn to the meat, and the next couple of boxes here are really important decisions that you have to make. So by default, auto scale is enabled, and in this particular case, we're going to get a Spark pool which starts at 3 nodes and goes up to 10. That means that when the pool starts initially, you'll get 3 nodes, and then it will scale as many as 10 nodes based on the workload that comes in. We're about to change this to 5. The reason we chose 3 is because it's the cheapest option. And being a Scotsman, of course, that was important to me, and so that's why we went with 3. That's the smallest size we support today until we go ahead and do the 1 node work that we were being asked about earlier on. The downside of 3 is it doesn't actually leave you that much horsepower to go ahead and run jobs. And I'll explain why when I pop back to the slides. And so 5 gives you more horsepower, because what's happening for a lot of customers, we see this in telemetry and also feedback that we get, is people are sending 1 notebook, which is not that big, to the Spark instance that gets created, and it goes ahead and runs. But if you submit a second notebook, then it takes 2.5 minutes for the second notebook to actually run. And you're like, hey, what happened? This thing's running, I just submitted more work to it. Well, what's happening there is auto scale is kicking in. And to auto scale, we have to add nodes, and that's a minimum of 2.5 minutes because it's the same startup time. So that's why the notebook takes 2.5 minutes to run. And so if you run out of resources on 3 nodes, we'll continue to go to 10 nodes, but you'll pay the price of the 2.5 minute start time every time we expand up. And so that's one of the things that we're going to go fix. And so you can enable or disable auto scale. We'll just leave the default for this particular one. If you disable auto scale, I hate that. That will be a bug I'll be filing after we're done here. So if you disable auto scale, here we go, then you just pick a fixed number of nodes. Now, the advantage of auto scale is we don't spin up the nodes unless we need them. If you go ahead and don't use auto scale, then we actually spin all the nodes, whether you need them or not. It does mean that you get faster response time on that second and that third notebook because we're not having to auto scale. But we spun all the nodes and you pay for them. So this is the balance between cost effectiveness, which autoscale is very good at doing, but still ultimately gives you the same compute power. It just takes longer to get there. Or, hey, I just want predictable stability and I'm willing to pay more for it, in which case I'm going to go with the standard non-autoscale machine. Okay, so that's that. And that's really, those are two very critical decisions. And we'll show why some of that's critical in a second. Okay, so what do we have as extended settings? Well, we have enabled auto pause. You really want that on. You can drop this down as low as 5 minutes if you want to. Which version do you want? Well, there we go. There's 2.4 and 3.0 in preview. We're just informing you here of the different versions. If I choose 3.0 by GA, I'll get a much newer version of Python. I'll get a new version of Scala as well. I can submit configuration. So if I want to change the Spark configuration, Spark has over 200 settings, some of which can be very important in terms of performance and capability. You can give us a text file. You can do it in code later if you want to, but here you can just give us a text file and we'll take that. And I can also specify what I want to do about package management. And I'm not going to get into details of that. We got some good docs on it and it takes a little while to explain all that. So let's go ahead and we'll review and create. Information is missing and not valid. Oh, great. Did it mess with the name again? Oh, let's go back to basics. Really? You don't like that at all, do you? Okay, that would be a bug that we deployed. Luckily, I've created one of these before. Very interesting indeed. I'll have to kind of work out what's going on there. So it's not very exciting. We're just going to provision the resource and we'll go ahead and I'm just going to move March out of the window. We'll go ahead and create this resource, which remember doesn't actually do any work, but goes ahead and just defines the metadata. And I can go create 10s of these with different settings. You know, lots of people have some autoscale clusters and some without autoscale. They have different sizes. For example, let's say I don't trust Mark. And because I don't trust Mark, I'm not going to let him have access to a particularly big cluster. Maybe he only gets like 3 to 5 nodes. But Victoria, I really do trust, so I'm going to give her access to 100 node. You can also use Spark pools as a way of doing sort of cost management by cost center. So you can have dev test and production, different Spark pools with different characteristics. You can also have, hey, here's this cost center and they get access to these Spark pools, and here's a different cost center and they get access to these Spark pools, and then we're good to go. Let's discard changes there so we can drop out. All right, we're going to go back to slides for a second to explain some of the things that I just talked about because they're a little alien sometimes. Okay, so how do Spark pools work? So here we have user 1 submits a session and submits it to Spark pool A. It actually submits it to the cluster manager, but conceptually we're submitting it to Spark pool A. The Spark pool A says, hey, is there a instance already running for this user and Spark pool A? And if there is, then you connect to it. And you'll see the Spark instance name is automatically generated and managed by us, because you never connect directly to an instance. You always connect to the pool. And then we return the Libby session ID back, and you can go ahead and submit jobs. And so user 1 has their own dedicated Spark instance right now. It means there's no side effects from other users. It's very predictable in terms of performance. Now user 2 comes in and says, hey, I would also like a Spark pool too. So let's say this is Mark coming in at this point in time. And the cluster manager is going to say, hey, there is no instance with your name attached to Spark pool A. So I'm going to spin a new instance that is the Mark instance, and it's going to work exactly the same as the first instance, except it's a different one. You're going to get Libby session back. You can submit work to it. So now we have 2 instances, and these are personal instances of Spark. We get security isolation and we get resource isolation by doing this. That makes the system very predictable. What you're going to say, oh no, that's going to be super expensive. Everything's going to get its own instance. Well, not quite. Because if user 1 now comes in and says, hey, I want to submit another piece of work to Spark pool A. We go, oh, you already have an instance running. And so we're just going to connect to that and use that. We may need to auto scale it or something like that. And so these are personal instances. Now, for development, everybody gets their own. When you run in production, like when you're being called from Synapse pipelines, we use a system identity. Actually, we use an MSI, and therefore there is a single instance for everything that's going on there. Data flows inside of Synapse actually use Synapse Spark, not Databricks Spark, and you can see that. And that's what happens there. So everything gets submitted using the same identity or a couple of different identities, and you get the work done. So think about a Spark pool as a per user budget, because you're constraining it per user on their instance. And at the workspace, then we manage things at per team level. All right, let me keep going. Okay, so let's explain how we get some of our fast start and why 3 nodes is probably not the best choice to start up with, as we've discovered. So here we have the definition of an instance, and we can take a look at it, and we have the base nodes or the system nodes, and then we have additional nodes. So it's a 3 to 5 in this particular case. So one of the ways to get fast start, you'll notice I never specified a head node and worker node definition. I just specified a node definition. So our nodes are homogeneous. But what happens is we make our request to Azure, say, hey, give me a bunch of VMs, please. And we actually ask for more than we need, and then we just wait for them. It's a competition as to which VMs come up first. And the advantage of this is that when you do this, the first node that comes up becomes base node 1, and we deploy Livy and Yarn and Zookeeper and everything else like that to it. The second node that comes up is the second base node, and it gets a little bit less in terms of system services. And then the last node to come up becomes number 3. So that effectively is a 3-node head node if you were using a different system with all of the management there. But each of those nodes can also run executors. And so they actually will do work, but not a ton of work because, for example, node 1 is doing lots and lots of work. That's why the driver will get allocated on that particular node. And so now you see that we have limited execution capability on those first 3 nodes. And if we expand that to 5, now all of a sudden we start to increase the number of executors that we can. And these are medium-sized executors. You'd have more executors if you used a small in this particular case. So this is expanding from 3 nodes to 5. And that default of 5 is something that we're going to go ahead and do. You can still specify a minimum size of 3, but we'll default to 5 just for giving you a little more horsepower. All right. That's that, and now we'll go back to the product again.
Can I ask a question? I think there was
no, you're not allowed. You can ask one on behalf of real users, but you're not allowed one, Mark.
Jeffson.
Yep.
No, all right, okay. All right, it was me asking the question.
Ah,
sorry.
You're pretending to be somebody else just so you get an answer back.
Yeah.
All okay. Right. So let's go ahead and run this, and I'll explain what we're going to go ahead and do here in terms of the code. The session stopped. I had it warmed up a little bit earlier, but the instance is shut down automatically to try and save money. So we appreciate that. And it's going to restart the session. Okay, so let's take a look at what I'm going ahead and do here. Now, I'm sure you've seen notebooks in the other sessions. I'm sorry I didn't feel like sitting up till 4 or 5 o'clock in the morning to watch all of the fabulous content that's gone before, but everybody should know what notebooks look like. And here we're going to do a very simple operation. We're simply going to read from this location, which is a storage location, and it's our retail demo data. The thing that's somewhat unique about this operation is this piece of it here. For those of you who use Spark and use notebooks, you're like, hey, that's not the real fast, easy way to write a read operation in Spark. And you can see now we're running again. So that was just a session restart, not an instance restart in this particular case. And so we're asking for Delta, which is a specific format. Now, if you know about some of the challenges which happen when you're going ahead and dealing with things like GDPR and updates to big data systems, it's incredibly hard to do. It's even harder to do well and in a consistent way that all the auditors will sign off on. So Databricks introduced this format, which is based on Parquet, which is the default format of the lake really these days, and actually is Spark's default format, although it's switching to Delta now. And what Delta gives you is basic transactional capabilities over the top of Parquet. And so the transactions are tracked and the transactions are applied. And one of the most important features, at least from my perspective, that we have on the Delta side is we have time travel. So this particular data set's had 20 or 30 transactions applied to it. But what I want is I want the version 0 of this data set. I want the one that we started with. Now I can ask for it by time. I can ask for it by transaction ID. Here by saying 0, I'm saying give me the version that is the start of time as opposed to any of the later ones. Okay, so now we're loaded in to this data frame store demographics. We'll go ahead now and we'll do something else slightly unusual. So I'm sure everybody's used to seeing read a CSV file, read a Parquet file, read an ORC file inside of Spark. Here, what we're actually going to do is we're going to connect to Cosmos DB, and we're going to read data out of Cosmos DB using their OLAP layer, which gives an OLAP or a kind of rectangular data view over the top of the document store. This doesn't cost anything in terms of resources. We're not going to slow down your operational store if you're using Cosmos DB, because it actually uses additional resources to do the work that are not the ones which are being used for transactions. And the nice thing about this OLAP interface is we end up with another data frame. It's just that simple. The data frame is the kind of language of choice for data inside of Spark and inside Python as well. And so we pull back another data frame. And then we're going to go ahead and we'll pull back another data frame, also from Cosmos DB. So what we have is we have a bunch of retail data about products, and we brought one of them out of Delta, and we brought two of them out of our transactional store. And what you do when you have three data sets, well, of course, you go ahead and you join them together. And here I'm using a little trick that if you've never seen this happen in Spark, then it's a good one to have in your back pocket. I know that one of the tables is very small. And instead of doing a shuffle and shuffling all the data around to do the join, which is incredibly expensive in a distributed system, we're going to do a broadcast. And what a broadcast does is it takes one of those data frames and it puts a copy of it in memory on every single node in the instance. And so now all the joins can be local instead of having to be shuffled and swapped out. And you'll sometimes see the query optimizer will introduce broadcast joins when it's smart enough to do it. But if you know your data better, then it's a pretty good idea if you want to go ahead and do the broadcast join. Now, if that DF products table grows too big, then you'll actually start to cause problems. So you just need to keep an eye on it. All right, so we've gone ahead and we've joined our data set. We have a nice rectangular one. I won't go through displaying the results. You'll work that out. I'm going to drop a bunch of weird titles. By the way, this data is the retail data, as I said. We're going to use a different data set a little later. I'm going to rename a bunch of columns so they're actually useful. I'm also going to add a computed column in here. So here we go, and we're going to create a computed column here. And I'm not even going to bother printing the schema because it's not that interesting. And then we're going to go ahead and display it. Now, one of the things you'll see down here, I go ahead and collapse this in on the left-hand side, is when we do the display, you'll see that you don't get the usual horrible kind of Python display output. You get a nice pretty table that's scrollable, and you can sort the headers and things like that. And so that's a custom control that we built. You can still use head and controls like that to go ahead and display the data if you're used to it, but that will give you a nice view. We can also do charting in here. Now, this is not designed to replace something like Power BI, but it is designed to allow you to take a quick look at the data. As you can see, we need to do some work on our defaults in this particular display. So let's go ahead and change some stuff up here. We're going to add a little line chart here. We change the store key to week starting because we want to look at the data over time. The values we want to look at, there's actually the quantity. So we're going to look at the quantity sold of the product. And then the series group, we actually want to be the product code. So we want to compare different products and how they're doing over time. And then we're going to do that sum, and that's just fine. So let's go ahead and apply that. And immediately you can see it's a little rough in terms of charting. Like I said, it's no competitor for Power BI, but I can see, you know what, I think my data's right. I think my data prep has worked. I think the data is somewhat clean. I can see the different SKUs here that I know. I can see that Surface Laptop 3 is winning, but that Surface Pro 7 was winning in terms of sales. And so that feels about right to me. So I feel confident that I can go on with this data process that I've got here. Okay, so we're going to head here. We'll create a table in the catalog. So we're doing it. We've been doing everything in memory up until now. So we're going to save this as a table. And once we save this as a table, there's a couple of interesting things we can actually go ahead and do with it. So we'll wait for this to finish writing. There we go. So the first thing is now I can use Spark SQL against this. So if you're more familiar with SQL, which I'm guessing a lot of people are, given the nature of this event, then you simply go ahead and you use the magic, that's what these are called, and you go ahead and run SQL, excuse me, and you're going to go ahead and get a result. Now, I'm not going to go through showing the results viewer and those sorts of things. We've all seen that before, and it's going to look remarkably like this one up here. The other advantage of going ahead and providing you with a table is if I go up here and go up to storage, well, databases, and if you see down here, this table here has been created, and it's Surface Sales Featured DF. If we scroll down to here, you'll see Surface Sales Featured DF. Spark uses lowercase only, so the case is converted when we do the save. Okay, so we created a table, but we know that because we ran the %% SQL sign. Let's go ahead here, run a new SQL script. We'll do select top 100 rows, and we'll go ahead and run it. And I saw that some of the questions were being asked by our team in Serbia earlier on about SQL Serverless. So this is actually using built-in, which is SQL Serverless in this case. And I'm going ahead and querying the data, and that results viewer looks remarkably familiar. There's also a charting viewer. which also needs some work on the defaults. But just pause for a second and think about what I just did. So I read data from a Delta table, which was a transactional table. I read data from an operational store, which are actually two tables in this particular case, which was stored in Cosmos DB. I did a bunch of data prep magic. I could produce a new data set that I can use for BI, for ML, whatever I want to go ahead and do with it. And then I published it. And I published it back into the catalog. I could have saved it to the file system as well, but I published it back into the catalog. And SQL Serverless and Spark share catalog. The information is shared between the two. And so by writing that table into the catalog, SQL Serverless is able to view it and it's able to query it. So this is part of what I was talking about when I said we're a job service and there's no JDBC connection, there's no ODBC connection, because it is so seamless to be able to write into a place where SQL Serverless and eventually SQL Dedicated will be able to read the data from. And most people prefer a SQL interface to doing this kind of interaction with data and not PySpark and Scala and C#. And so that's what we've gone ahead and provided here. I'll pause there for a second and see if Mark's got any questions before I go into the next phase of the demo.
Yeah, we did have a question about, if you're doing SQL queries, is there a way to implement a broadcast join?
Using Spark SQL, you know what? That's a really good question, and I don't know the answer to that. Right. That's one I'm going to have to go look up. So congratulations, have a free drink on Mark or whatever it is for people who can ask the stump the expert question and win. But yes, I don't know. I've never done it using PySpark or Scala, I'm afraid. So I'm cheating from that perspective. And now I'm going to have to go look at the docs as soon as we get finished here.
Cool. Thank you.
All right, and congratulations on Mark giving away drinks. Okay, one of the things that a lot of people get a little confused by when they deal with Spark, and this is Spark in general we're talking about now, not Synapse Spark, but it's good to get a good handle on this, is partitioning and executors. If you get these two dimensions wrong to your data, you will have terrible performance. If you have these dimensions correct, you will get amazing performance. So to give you an idea, there was recently an external customer we worked with, and they needed their data processing to run in under about half an hour. And it was taking an hour and a half inside of Synapse. And we're like, oh, what went wrong? So we took a look at the data set, and they were using an interface where they wasn't using eventing, but they were making lots of small writes. And so they had hundreds of thousands of files which were being read by Spark in directories. So Spark is notoriously slow at recursing directories, at least in 2.4. There's a bunch of optimizations in 3.0 which make this much better. And so the majority of the time when we profiled it was actually being spent recursing and navigating directories and not actually processing the data. And so what we did was we asked them just to use Linux file system commands as part of their batch job to concatenate those files together so that we had much smaller number of files. And we went from an hour and a half to a minute and a half. That's how big a difference the size of the file can make to the performance of the system. So while this session is starting off, I'm just going to pop into Excel for a second and show you something in Excel. So this is a chart that shows, except it's, let me just, whoa, that's not what I meant to do at all. Let's do view, and we'll zoom out a little bit. Zoom out. No, it's still not enough. That's what I get for changing my desktop resolution. 200%. Oh, no, I got that wrong. It's 2 o'clock in the morning here. I always forget which way we switch. There we go. Now we got it. Okay, so I've got two pivot charts here I'm going to show you. The first one has number of executors along the bottom, and it goes from number of partitions. Along the bottom, it goes from 1 to 100,000. And this is the taxi cab data in New York. So let's go ahead and we'll take a look at write time because we did all the writes first. And if you take a look at this, then actually writing one large partition is slightly more expensive than writing 10 or 100 because we have limited ability to do parallelism there. But you can see if you go from 10,000 to 100,000, that's way more than an order of magnitude growth. So 100,000 partitions starts to get very expensive to go ahead and run in this particular case. So not only from a perf perspective, as I was describing earlier, but it's something you have to be careful of. If we go ahead and take a look at the read time on this, You'll see the read time is pretty consistent, at least from 1 partition up to 1,000 partitions. So a little bump at 10,000. But once again, we see a pretty significant jump when we get to 100,000. And these 3 different bars, 3 different colors, are different sizes of executor. So it's different degrees of parallelism. An executor in Spark is something that gives you parallelism by having memory and threads associated with it. So if we go in here, we'll see we have blue is large, which is 9 executors. Each one's using 144 cores. Medium is 19 executors with 152 cores. And small is 39 executors with 156 cores. And so from that perspective, you can see the different sizes that we have here. All right, that's that chart. Let's take a look at this other chart over here. So you'll see on this chart, the one difference, and it's probably hard to see because of the zooming, there's a 4 here. So let's take a look at the right time. And I'm going to, well, not the right chart. I'm going to take a look at the 4 and explain it in a second. As you can see here, this is exactly the same as the chart that we just saw. But having 4 partitions in this particular case is way slower to write than 10, 100, 1,000, and even 10,000. What on earth is going on with that? Well, this gets even more dramatic if we do this. And here you can see that the read operation in this particular case is taking way longer. So when we do these partitions here with numbers, I'm simply creating a partition using numbers. And I'll go back to the UI and we'll take a look at that. There we go. There's the demo thing. So I'm not going to run all this code because it will take a little bit of time. So if I do many files, yeah, thank you. So what I'm doing here is I'm simply turning around and I'm taking a data set and I'm saying, I'm going to repartition you, and I want one partition. Then I want 10, then I want 100, then I want 100,000. So you can see all the different sizes of partition in here. Here's the 100,000. What I'm doing with this last one that you see is I'm partitioning by column. And so if we go in here, we'll see we're reading the same data set, 50 million rows in this particular case, and we're saying partition by year, month, payment type, and vendor ID. So year and month are good partition keys in this particular case. Remember that the way that the storage works here is you'll end up with a directory for each one of these. So we don't have too many directories. We're not working too deeply here. But payment type is credit cards and different types of credit cards. Well, all of a sudden, you start thinking about the cardinality and the number of directories you're creating. And if I'm going by year, by month, and then a directory for each different type of payment, that's really going to start to increase the number of directories I'm going to recurse through. And by using vendor ID, those are the different companies that supply yellow cabs inside of New York. There's a lot of them. And so actually the number of partitions and the number of directories increases the lower that we get down the stack. That is a truly terrible way to design a partitioning scheme. And the reality is, from a query perspective, and an aggregation perspective and a partition elimination perspective, if the majority of my queries are filtering on year or month, or I'm aggregating on year or month, then that's going to be pretty powerful. I find it unlikely that we would filter or aggregate on payment type, maybe, but we certainly wouldn't do it by vendor ID in this way. We do it a different way. And so you can see there, and this is what I mean by 4 partitions. So if we go back to Excel, this is the 4 partitions, because we're creating 4 partitions, but we're not creating 4 files in this case. We're creating a lot of files. It turns out thousands of files across a 4 deep directory structure. Now, we haven't finished our 3.0 implementations yet, and it'll be interesting to compare these numbers on 3.0 versus 2.4, because 3.0 should be much better at this because of the recursion improvements. So that's just a tip for Spark in general about how to go ahead and make things a little bit better. Okay, how are we doing on time? We got a little bit of time. Okay, so let's go ahead and take a look at Delta Lake. So let me start here. Again, we got a session stop, so we'll go ahead and we'll just show you what we're doing here. We're just going to generate some random numbers. We're going to have a delta path to where we're going to save the data. I'm going to go ahead and say, here's what I want the data to look like, show it. You can see it's very simple here. It's numbers of 0 to 4. And we're going to go ahead and write that into a delta table, which, remember, a delta table is the transactional table. So we're going to read it back in again, and it's unordered because it wasn't unordered right, and so it just comes in an almost ordered order, but not quite. All right, what are we going to go do? So what we're going to go ahead and do here is we're going to go ahead and we added more data. So we added 5, 6, 7, 8, 9. So we created more data and we've written it back out again. And so now we've got this data frame with just this data in it. If we go ahead and look down here, what you're going to see that we're going to do down here is we're going to take all the even numbered examples, and we're going to go ahead and we're going to add 100 to them. So we have 106, 108. We go ahead down here, we'll say we want to filter out in this particular case. I'm going to show, so we'll only get the odd numbers in this particular case. Now, this is where life starts to get interesting. We're going to do a whole bunch of manipulations on the data. I'm not going to go through this in the interest of time. But what we're going to do here, I scroll down, no, get the right scroll handle, here we go. So here we're going to say, show me the history for this particular table. So remember, we started with 0 to 4. We added some bigger numbers. We messed with the number twos, the evens, and added 100 to them. Then we messed around and filtered some out. So we did a whole bunch of work. And so this is a single transaction here. Unfortunately, it doesn't format very quickly. It's something that we've got to do some work on. And so here you can see what's the transaction number. In this case, it was 4. What was the date timestamp on it? It was a merge operation in this particular case. You can see what predicate was applied here. How many rows were inserted into the table? How many files were added to the table? Number of target rows updated. And you can keep following these transactions. And yes, it's not the easiest thing to read, but it's pretty logical as transaction logs go. And you don't need a special tool to read it or a browser. It's just simply text that comes out. And here we can see transaction 0, which went ahead and created the file, which had 5 rows. Remember, we had 0 through 4. And then here you can see that first transaction where we also wrote 5 rows, but we changed the number within the file. Okay, here you can see another example of what I was playing around with earlier when I was doing the read operations. Here you can see us reading the Delta format and asking for version of, because remember the output up here, we're getting all sorts of crazy numbers. We got negative numbers, we got even numbers, we got odd numbers. It definitely doesn't look like the 0 to 4 that we started with. And here you can see, there's the 0 to 4 that we started with because we asked for the data as of transaction 0. We could have done timestamp, but in this particular case, we just used 0 because it was easy to get to. Now, the Delta Lake is quite complex in terms of the capabilities. In its most basic form, it's very easy to remember and to think about and all those sorts of things. But as you can see from the APIs, I'm flying through a bunch of APIs here in the interest of time. We have really good tutorials on this, really good documentation on this, lots of sample notebooks on this. And they're all written in multiple languages. I'm using PySpark here because it's what most people find relatively straightforward to understand, but we also have an implementation in C# that is a Microsoft-specific implementation. And then also there's a Scala implementation that comes with Spark itself. All right, so we have 3 minutes left. We've done a quick lap around. We've shown a whole bunch of different things, including a bug, which I'll follow when we're done here. But to summarize, we looked at Spark pools. We looked at the property of Spark pools. We looked at how important it is between static and dynamic clusters and choosing defaults. We looked at partitions and executors to make sure we understand how those have an impact on performance. And the answer is that small size is not huge, but the bigger you get, then the worse it gets, particularly when you get up into 100,000 partitions range. We looked at partition choices on data in terms of partitioning by data columns rather than just by number, and we saw the significant impact that that can give you. We took a look at a basic example where we just stepped through the notebook. We looked at the results viewer. We read some data from Cosmos DB. We read some data from Delta. We merged it. We did all the sort of usual things that if you were doing data prep in code as opposed to using Weihong's fantastic UI to do data prep, those are all kind of standard things you do: derived columns, drop columns, rename columns. And then we've gone through Delta Lake in very quick format, but it's just to give you a taster, because if you're interested in using transactional Parquet, then Delta Lake is something to definitely read up on and get into. And one of the reasons why it's really important to us is we recently announced a preview of SQL Serverless able to read Delta files. So that example earlier on where I wrote the data back out to the table, I could have also written out to the file system, that Parquet data, and SQL Serverless would still have been able to read it. If I'd written out in Delta format, it wouldn't have been able to read it because not all services can read Delta Lake, including in Synapse. Pipelines have support for Delta Lake, Spark has support, and now SQL Serverless has support for Delta Lake. So the nice thing there is you can write this transactional data and then you can go ahead and read it using your tool of choice, which is SQL Serverless, which works really well with Power BI. All right, that's 44 minutes of you and waffling. Mark, do we have any open questions?